Practice what you preach is a very famous saying, and of course it can be done in a different context. And Norbert will talk about date and times, and he's expert in date and times in a context of programming, although he said to me before presentation that he will not respect the time constraints. So I have to warn you. All right, Norbert Wójtowicz.
Testing 1 2 1 2 1 2 3. Okay, so this is just a test of the system. Actually, I just want to take a quick moment and give a shout out to this conference because every time I get invited to talk here, and they sort of know what's coming, this is how I envision the organizer of this conference look like, right? So like, just kudos. This is the actual talk. Like, cameraman, you can actually just start here. Okay, so time. The Gregorian calendar. So, this is me, and this is all the time I have for an intro. You can find me online, or even better, just talk to me at the after party. Today, we are going to be talking about the Gregorian calendar, and we are going to be showing code in C++. Why would we do this? Well, here's the pitch. I'm going to show you a bunch of history, and you will learn why decisions made thousands and thousands of years ago impact the way you work day to day. And we will take this opportunity and sort of use this as a jumping off point to help you build new intuitions on how to answer these complicated questions. How do I make computers go fast? How do I deploy breaking changes? And when should I do a rewrite? And I would posit that these are all questions that you are all have a burning desires to actually learn, right? So, a very short history of the world. In the beginning, there was the Big Bang. And then, many years later, we have the modern solar system. The Earth orbits around the sun, and the moon orbits on the Earth. This gives us a solar day, a tropical period, or also known as solar year, and a lunar month. These are very useful things for people, because it turns out we don't have good night vision, so you would like to know when it is daylight. You would like to know when to plant the crops, and when it's time to actually start, storing food for the winter. And you would like to know when it's, for example, low tide or high tide, which is something you need to look at the sort of the lunar phases to understand. So it turns out that as long as people have been around, people have been trying to predict these things. And it has been done with more or less success. So it turns out that the day is kind of easy. It's exactly 24 hours, or 86,400 seconds. To this very day, there is such a thing as a mean solar day, and it is defined exactly like this. So if you want to talk about like leap seconds and stuff, talk to me afterwards. But it's actually correct. The solar year, unfortunately, it's like 365.242,199 days. And I see that I tested this on a different projector, and so probably some of the fonts are going to be off already. I can already see this testing in production. But, sorry, that's a tangent. Lunar months. Well, it turns out that if you just have a lunar calendar, after 12 lunar months, you're going to have a year of 354 days, which is a problem because it means that every year you're drifting by 11 days, right? So as you can imagine, most civilizations sooner or later realize that these calendars aren't perfect. They end up having lunar calendars, solar calendars, or most often, a combination lunar-solar calendar because they sort of want to be able to predict both of the things. And by the way, a small trivia. The lunar month is usually referred to as 29 days, but actually it takes 27 days for the moon to orbit around the Earth, exactly. But what happens is that the way we observe the moon is by looking up at the sky in comparison to the sun. So in 29 days, what happens is those two bodies are orbiting around the sun as well. So you have this weird parallax effect, and we think it takes 29 days, but actually it takes 27. So that's why you have something called the sidereal period and the synodic period. And one more bit of trivia. There is this fun ratio of 235 synodic months is exactly 19 tropical years. This is completely useless information, except if you ever are digging into some code that's doing calendar math, and you see a magic number, 235, or a magic number 19, you will now know that what is happening there is a conversion between lunar and solar calendars. This is Stonehenge. We think of it as a very old thing, right? Like this is before the aliens came. And I sort of want to give you some context about how old this really is. So calendars, a brief history. In 11,000 BCE in Australia, we have a structure that is able to correctly predict solar movements and can predict when the equinoxes, the solstices, and so forth appear. In 8000, in Scotland, we have a perfectly working rock formation, like a rock structure, that is able to predict both the lunar and the solar calendar. The Sumerians only show up in 5500. They give us a lot of interesting new math. They give us a base 60 math, which is why, to this day, all the stuff you do with time and calendars is either is divisible by 60 or divisible by 12. It's because of them. The Egyptians, they've been around a little longer than this, but by 2700, it is 100% known that their civil calendar understood that a solar year is 365 days, and they had the concept of a leap year. Then we get to Stonehenge, right? Only then. So it's like relatively new. And we can argue if Stonehenge is used for calendars of observing some kind of astronomical things, or just human sacrifices, or maybe it's just the aliens. 1890, the Babylonians show up. They have a lot more new, interesting math for us, mostly based on approximations and derivatives and things of this nature. And they also give us the compass directions, so northwest, southeast. The Chinese actually go through many calendars, but the one in 1600 also guaranteed to be 365 days plus a leap year. And only then do we get the Greeks in 1200, right? And they give us math based on geometry, they give us logic, they give us philosophy. Why am I talking about all this? What I'm trying to give you is some context that humans have known many of these important things for a very long time, but then the Romans show up, and we forget everything, right? The Romans are essentially the Silicon Valley tech bros of the ancient world. They have a serious case of not invented here syndrome, and they refuse to use any of this previous knowledge. So you will see in the upcoming slides what their calendar actually looks like, but I want to sort of give you some context about why the world exists today as it does. Because the Romans, they cared, their KPIs and their OKRs were military expansion. So law, medicine, agriculture, building roads, building aqueducts, like grade A, they're really good at it. But anything that wasn't for military expansion, they don't care about, like philosophy and all this stuff. So what happens is they lose all this knowledge that we've gained. You know, like the Library of Alexandria burns down like halfway in 48 BCE because of Julius Caesar. But actually, what people don't know often is that it didn't get burned down completely. It got reconstructed. What actually happened was the Romans took over later in history. They took over Alexandria, and they actually let the libraries go into disrepair. They kicked all the scholars out, and the stuff got destroyed due to neglect, not by accident, because they simply didn't care about this. So thankfully for us, there's like a weird multiverse comic book like DC situation going on, and the Arabian Peninsula, they're actually keeping all this knowledge around, and they're advancing it in many ways, right? We've got like the Treatise of Algebra in 1830, CE, by the way, CE already. And this is important for Europeans because in 1200, there's something called the medieval Renaissance, when basically the Roman Empire is it's like falling apart, and we're getting like a trickle of all the stuff from the Arabs, right? Obviously, there's lots of wars, conquests, and stuff like this. But the nice thing is, we're also getting all that knowledge coming in. Europeans learned about ancient Greek philosophers like Euclid and Aristotle by reading Arabic translations of the original works, because it was lost during this time because of the Romans, right? So let us look, with that context in mind, let us actually look at what the Romans did. Okay, so 753 BCE, this is the beginning of Rome. The Romans have a 10-month calendar. The first 4 months are named after the gods, the most important ones. And then they ran out of creative juice, or they ran out of GPT tokens, and they just numbered the months. All the months in orange are literally the name of the month of the year, right? So October, octa, 8. Decimal, December, 10, right? All those months literally just mean the name, like the number of the month, okay? And each of the months was still like 29, 30 days base because they were still kind of on the lunar calendar. So as long as the year was like basically 300 days, but obviously the year is not 300 days. So what they did is they called the rest of the time winter. They didn't count it. It's like they just went into their home and basically came out 2 months later when someone like raised their hand and went, today's the 1st of March. And on top of this, the Romans, they didn't have the concept of days of the month. You didn't say something like, it's the 8th of March. What you had is you had the counts, the nones, and the ides. Now, Historically, they are actually based on lunar phases, but in practice, they had nothing to do with them at this point. You can think of it like the Calends was the 1st of March, Nones was the, let's say, 5th to 7th, and the Ides was around the 14th. And then all of the other days of the month were just relative numbers. So you would say, I'll talk to you 4 days prior to the Ides of March. Like, that's the way you would talk, right? And by the way, it's funny because Calends, Nones, and Ides actually means phases of the moon, but in fact, this is the equivalent of us using a floppy disk icon to save things to the cloud, right? Like, they have nothing to do with each other anymore. And it's relevant for the future because they didn't like the zero concept. Their calendars are one-based. Okay, so after 50 years, they get tired of this idea that they had this unknown winter period, and they add 2 new months. January goes in the beginning of the year because rough translation, it's looking forward to the year ahead. And February goes to the end of the year because rough translation, it is looking back. It is a retrospective on the year that has passed. This is why February has the least number of days, and this is why the leap year calculation is in February, because it happened at the end of the year, right? You basically ran out of days because you wanted to start a new year. Makes sense, right? It's a little weird because they still don't have the concept of 365 days, and now Okta means 9 and Deci means 11, which I'm sure didn't confuse anyone that was living during that time period. But that's not bad enough, because in 450, the Decemviri, which you can think of like roughly the Senate, they were going to get voted out of power. So what do? By national decree, they voted that February is the 2nd month of the year, and they're still in power for another 10 months. These guys wanted to stay in power for 10 months longer, and 2,000, 3,000 years later, we're still dealing with the consequences of this change, right? This is where we're getting the calendar from, by the way. So, okay, 45 BCE, Julius Caesar shows up on the scene. So Julius Caesar has been spending a lot of time with Cleopatra, for obvious reasons. And the Egyptians have a calendar that, as I mentioned before, like 2700 BC, they already knew this. They had a calendar that was 365 days, and the way they did it was they said, every month is exactly 30 days, and then we're just gonna have a 5-day New Year's Eve party. And when it's a leap year, we have a 6-day New Year's Eve party. Imagine all the times you've been dealing with some calendar issues. Imagine like this was the rule. Every month is exactly 30 days. There is nothing more to compute, right? So Julius came back to Rome with these ideas, but of course, it's like, take theory and put into practice. People didn't want to get rid of their old things. They had certain holidays that happened on certain days. You couldn't just mess with that. So what he ended up doing was he needed the 365 days, so he put an arbitrary number of days into each month to piss off the least amount of people. And that's why certain months have more days than other months, right? And he defined the idea that, there's every 4th year is a leap year because of the, the drift. Unfortunately, literally a year later, he died on the Ides of March. Now you know that the Ides of March just literally means a specific day in the month. It's nothing more important. So he died, and the Romans, because they count from 1, not 0, looked at that rule and said, so every 3 years, I should add a day, right? And that's what they did. So after 40 years, the calendar has drifted again. And the next Augustus Caesar goes, no, enough is enough. We're going to fix the fix. So they made another calendar reform. They fixed the actual problem, which is they said, every 4 years. Yes, every 4 years, exactly. Now you get it, okay. So he did that, but since he was already doing some calendar reforms, and he had kind of an ego trip, he named one of the months after himself. That's where you get August. But also, to not look like a complete douchebag, he renamed the previous month after Julius Caesar, right? And that's where you get July and August from. And this is what is now known as the Julian calendar. It was actually Augustus that proposed it. And that's 8 BCE. And apparently the way we learn about it in school is that's the most important date, like that's the only date. And then somewhere in 1600, specifically 1582, Pope Gregory shows up and he does the Gregorian Calendar reform, whatever that means. Oh yeah, that's it's divisible by 4, except it's divisible by 100 or 400. What does this all mean? Okay, so after he added all these rules, we'll talk about those rules later. We get the more modern version, which is the 365.2425 days average, which, by the way, is still a drift, right? There's still some drift involved. But we'll come back to this later. So I realize there's actually a lot more interesting history, but I wanted to sort of highlight how we learn about this in school, which is that there's a Julian calendar, then there was a Gregorian calendar reform, and then there's the modern day, and apparently nothing happened in between, right? Obviously, like, what else could possibly happen? We will come back to the interesting parts of the history, but I do want to give your brains a little break, and I want to talk about computers for a minute. So how do we make computers go fast? Imagine you're straight out of the university, and you're at your first hiring job interview, and you get this question. Implement a leap year function, right? So a function that returns whether a year is a leap year or not. I'm not even asking you to write the code. Like, the code is right there. What I am going to ask you, though, is this the fastest way you can write this function? Like, it seems pretty fast because the first thing you do is you immediately check for 4, which happens 75% of the time, and immediately return. Next, you check for 100 and immediately return. Next, you check for the 400 modulo, right? So it seems like as fast as possible you're returning from this function. Now, obviously, if this was this obvious, it wouldn't be on a slide. So I will actually tell you that this code on the right is faster than the code on the left. But the code on the right does more operations more frequently than the code on the left. So why is doing more work on the CPU faster than doing less work on the CPU? Any thoughts? You have 10 seconds because we've got a lot of slides. So the problem, I heard many things at once. The problem is the if. If is entropy. And entropy hurts the branch prediction algorithms that modern CPUs have. And it turns out that on a modern CPU, there's only so fast you can make the chip go, right? Like, we're hitting the limits of physics. So until we switch architectures yet again into something different, we're hitting the limits of physics. So you can't make CPUs much faster. What you can do is you can make more of them, like more cores, more dies, and so forth. And you can parallelize things, right, with different kinds of pipeline strategies. But branch prediction breaks all this because it means that all those things that were almost going to run to completion, there's a go-to statement in there. It has to jump to some other part of that code, and it has to ignore everything it just processed. So it turns out that in some ways, on a modern CPU today, for some simple kinds of micro benchmarks like this, it is actually faster to do more work than it is to do less work. These, by the way, are just 2 ways to write this code. They're equivalent performance-wise. But they're 3 times faster than the code on the left, right? This, by the way, obviously I understand is not a C++ conference. I do not expect you to learn about C++ profiling and benchmarking. I am not the person to teach you. What I want you to get out of this talk is 2 things. First of all, your intuition on what is fast and slow on a CPU is wrong, by definition. Because even if what you have is right, it's not true 5 or 10 years later, because the architectures change. So the only way to do performance monitoring and benchmarking correctly is to actually benchmark. Have a hypothesis, test before and test after. And don't be afraid to try crazy things, like doing more work instead of less work, right? Quiz number 2. Here's a function, and it says, give me the number of days in a month. If we are in the Egyptian calendar, this would be a constant that returned 30. And you can inline it. But we're not on the Egyptian calendar because of the Romans. We are instead on the Roman calendar. And the Roman calendar, every month has a different number of days, and then you still got to deal with that leap year thing. Can we make this code go faster? Because if you look at it, what we have is we've pre-computed the values. It's a lookup table in a vector. Can you get faster than a pre-computed value? It turns out you can. The way you do it faster is you do more work. It turns out doing more work is faster than doing less work. Again, ideas why? Memory access. This is slow. Again, the more cores we have, the more CPUs we have, our memory is getting slower and slower compared to our CPU. On cases like this, where we're just letting the computer do what it does really, really well, it's actually faster, because even if you didn't have a cache miss, this means that your CPU is using up critical L1 cache to store things that it could have been using for other things as well. And again, it's not intuitive. 5, 10 years ago, the code on the left might have been faster, right? The point is that you have to rethink any assumptions you have about performance every couple of years because everything is changing around us. Okay, quiz number 3. What is an epoch? It's not a trick question. What is an epoch? It's this weird number, right? I give you a weird long number and I tell you this is an epoch, then the first thing you do is you go, this is the number of seconds since January 1st, 1970. Wrong. If someone gives you an epoch, which is this big integer, the first two questions you need to ask is, what is the granularity? Are we talking seconds, milliseconds, nanoseconds? And the second question you must always ask is, what is the start date? Because depending on the API, it may be 1970, it may not be 1970. It may be January 1st, it may not be January 1st. These are bad assumptions. Different APIs have different understanding of epochs. But if I tell you that this is an epoch, January 1st, 1970, then it's fun because you can use very basic math to pull out lots of interesting data out of this thing, right? You can find out exactly which hour, minute, and second this integer represents, and you can even get the weekday, because it's a module of 7, and it happens that January 1st, 1970 was a Thursday, right? Simple enough. So here's my question. What do you divide by to get the fact that it's April 12th, 2025? You know the answer at this point? The answer is, you can't because of the Romans. If we had a simple system, like the Egyptian one, we could simply do a bunch of division and we'd get the answers, but we can't. This is the best we could do. A lot of smart Microsoft people sat down. .NET 6, this is a pretty recent version of .NET, right? .NET 6, this is the best that Microsoft researchers who are paid lots of money came up with. It's got memory lookups. They actually independently computed the leap year version and the non-leap year version. It's got a bunch of ifs, and it's got a while loop. This is the best they could do, right? So the question is, how can we do better? And here's the intuition I want you to build. When you are working with a performance problem, or any other kind of problem, you're working on a domain problem, and it looks complicated, I want you to learn to rephrase problems. This is just like in school when you learned how to switch between the polar and coordinate and the Cartesian system. Some problems are simply easier to solve in one or the other. Let me give you some examples. Convenient data structures. Christian Zeller, 1882, came up with what is known as the computational calendar. Here's the idea. This is your calendar, right? 2025, January to December. And February is screwing us because of the Romans, right? So what did Zeller do? Well, he said, no, screw that. I'm going to literally just move the start time to March. And the year ends in February of next year. I'm going to do all of my calculations, all the math I'm interested in from a calendar perspective on this simpler model. The February thing is all the way at the end. I honestly don't have to care about it almost never, right? And once I'm done with this logic, I just move the goalpost back and get the answer I wanted. It's such a simple idea, yet nobody thought of it until 1882. Here's another one, convenient numbers. Very quickly, without thinking, what is 42 over 5? It's not an easy answer, but here's another question. What's 42 times 2? What's 84 over 10? Why is that so much easier? Because we are used to working with the decimal system, and we're used to doubling things. It turns out that for humans, n over 5 is 2 times n over 10. It's easier. By the way, thank you for your participation. Computers are like this too, except they have a slightly different logic. For them, bit shifting and big numbers are useful. So this is actually the fastest way to write n over 5 on a modern CPU. It's approximate because it's mathematically not correct, but because of how underflow and overflow works, it actually gives you the right answers, always. Okay? So this is basically this is the equivalent of Shimon's example, but for the CPU. There's a third thing we need for this specific task, but this is like Euclid affine functions. This is outside of this talk. But if you're curious about it, go Google it. I'm going to give you the 10-second elevator pitch. You know how sometimes low-level assembly programmers have like these fun tricks they do with bit shifting and operations to like trick the bounded boxes of CPU to get answers that they normally wouldn't get? Euclid affine functions are that equivalent for mathematicians. It's a way they rephrase problems to use bounding boxes to like make some kind of calculations easier. It's not part of this talk, but if you're interested, I highly recommend it. But the result is, using just those 3 changes, this is the .NET 7 code. This code has no ifs, no while loops, and no memory lookups. It's all just computations, just raw CPU, because of those tricks I just showed you that weren't that obvious. How much faster do you think this code is? Take a wild guess. 100 times? Oh, that'd be really good. No, it's 4x. The Neri-Schneider algorithm, that's .NET 7, and then .NET 6 is the 19.3. The Neri-Schneider algorithm is in the most recent versions of GCC, Linux, and .NET 7. Why do I say most recent? This was a white paper that was published 2 years ago. This is like bleeding edge computer science about how to make epic to date computations faster because of the Romans. Think about that for a second. You don't think this is important? Think about the server that's making 100,000 of requests a second, and due to our previous presentations, you're doing multiple logs per request, and every log, what is the first thing it does? It does this calculation to print out the date and time, right? 4x, that adds up quickly. TLDR. Branch predictions, memory latency are just examples of how modern CPUs are slightly faster and non-intuitively work different than, let's say, CPUs from 10 years ago. But I think the more important lesson for you guys is always measure, never assume, and learn to rephrase problems such that they are convenient for your purposes. Whether this is a performance thing or it's a domain modeling thing, there are multiple ways. This is very practical stuff. How are we feeling? Are we still here? We still good? Okay. Just checking in.
How often do you think about Roman Empire?
That's a party question. Okay. Deploying breaking changes. So let's come back to the history lesson. You're a very early Christian. When is Easter? The specification is Jesus rose on Sunday after the first night of Passover. That is the official that's the specification you get for a product manager to implement. So it turns out that the first thing that the early Christians have to do is they have to have a rabbi in their village, because otherwise they don't even know when Passover is, right? So obviously this was not ideal. So very quickly, 325, they come up with a better definition. They say it's the first Sunday after the first full moon on or after the vernal equinox. This way you no longer at least have to deal with the rabbis. This is called computus. This is where computers and computing comes from. Computus literally means the algorithm to calculate Easter. Your entire industry comes from this word to calculate Easter. This is the original big data problem. I want that to sink in. Okay, two things. First, a bit of trivia. If you ever are dealing with like scheduling problems and you have someone that defines a task as first Sunday after, you will now always remember, Norbert said don't do that. Why? Because you're immediately going to hit edge cases, which is, what happens if the thing I'm looking at happens exactly on Sunday? Do I count it or not? So here's the trick. Whenever you see something like this, you immediately rename it like this. And I apologize, but my fonts aren't working. The Sunday after the first Saturday on or after. It's a really simple trick, but this version doesn't have those edge cases you have to worry about, right? The second thing is, early Christians, not great fans of science. So they didn't want to actually deal with the whole solar, the whole predicting when the sun will be. So they actually just hard-coded it to March 21st. What could possibly go wrong? BD 725. He was both a devout priest and a scientist, and he actually developed a bunch of things. By the way, you don't learn about this in school, right? Because Julian Calendar, Gregorian Calendar. BD actually came up, he told everyone about the Julian drift, guys, we're drifting. This is not a good, strategy. We need to do something. 725, remember, 1600 was when they actually fixed this. Metonic cycle, he actually figured out this ratio that I mentioned. And among other things, he used all this knowledge to basically hand compute the next 532 years of Easters, right? There was no computer, so he was the computer, doing the computations for the computus. right? Finally, in 1582, Pope Gregory shows up, and they actually do the Gregorian calendar reforms. This is the BD algorithm converted to C++. And it has all these interesting things about, you see that 19, and you see all this other stuff that's sort of in the comments. We don't need to go through all the details. But basically, every piece of that code is basically someone at some point doing something weird to the calendar, and now you have to deal with this, right? Even that March 21st weekday, right? Like, if this was a vernal equinox, actually, it would be easier to calculate, but it isn't. So yeah, they have to hard code and work around the fact that it's hard coded. So yeah, great. And it's not a solved problem. So these are some examples of mathematicians that, famous ones, that actually have published newer, better versions of how to compute Easter, right? This is the never-ending struggle. The most recent paper, 1961, we're still dealing with this problem. We're still trying to find out a better way to actually calculate Easter. Yeah, but let's come back to Pope Gregory. So I know you all have this situation. You're introducing V2. How do you get everyone to switch over? You've had this, right? How do you get people to switch over? How long is it going to take? What are you going to do? Imagine your customer is not around for a year. Your customer has been around for 1,600 years. How do you get someone to switch off of 1,600 years of using V1? I think we have an opportunity to learn from the masters. First thing is simple and clear patch instructions. This is why you have that weird rule about divisible by 4, also divisible by 100 and 400. Because basically, instead of making up a new rule that people would then argue about, he took the old rule, which was divisible by 4, and he added additional patches to it. Because when you think about it, Pope Gregory had to explain this as an instruction, as a letter, had to send it out thousands and thousands of miles, kilometers away, and hope that someone who is reading that is educated enough to understand and properly apply this. Because otherwise, souls would not be saved, right? This is a big deal. So simple and clear patch instructions instead of rewriting and redoing the thing from scratch. If you're already doing a breaking change, take the opportunity to fix things you kind of wanted to fix for a long time, but you couldn't. So the March 21st equinox by now has drifted over 10 days, which means the Pope is in a weird place where he's saying that God is infallible, but the people are looking up at the sky, and the sun is 10 days from where it should be, right? So something's off. So he fixed it by basically just removing those days. He could have actually fixed it by switching over to the actual solar observation, but it is what it is. Another thing is, imagine you have daylight savings time right now. Well, most of us don't experience it because your iPhone updates it automatically. But imagine your parents having to actually wind the clock and remember to wind the clock, right? Or if you're on a Polish train, the trains literally stop in the field for an hour, right? Because they need to get to the train at the train station at a specific point in time. So imagine that, but it's not an hour. The person is going to go to sleep and wake up 10 days later, right? So they came up with this thing. They picked October 4th because it was a Thursday, so at least you would go to sleep on a Thursday and wake up on a Friday, right? You would lose 10 days, but at least maybe you could get sort of your work cycle figured out and then spend the weekend drinking and wondering what happened to your last 10 days. And slow adoption, so that he realized that this wouldn't be like a one-day switchover. So the rules were implemented in such a way to guarantee that people had over 120 years to implement this correctly. For 120 years, the Julian calendar and the Gregorian calendar would be in sync if you asked what year is a leap year. Because it's 120 years. That's got to be enough time. So you know where this is going. There's a wonderful Wikipedia page called the List of Adoption Dates of the Gregorian calendar by country. I'm just going to show you some highlights. Which countries do you think were the early adopters? Germany, Italy, Poland, Portugal, and Spain. These are the only countries that did it first day, immediately, switched over, bleeding edge. What do you think, how late do you think was the latest change? Remember, 1582, 120 years. 2016. But okay, that's a little unfair because it's Saudi Arabia, they switched from the Islamic calendar, right? And similarly, like some of these are Soviet Yugoslavian, so they were like switching from the Orthodox. But you don't have to scroll very far to, for example, find, Chinese switch from like the Chinese calendar, but you don't have to scroll that very far to find France, 1805. 1805. But actually, that's not the funnest thing about these. If we sort by countries, I'm going to first scroll and just observe yellow. Do you know what yellow means? Yellow means that someone switched from the Julian calendar to the Gregorian calendar, and then switched back to the Julian calendar, and then switched back to the Gregorian calendar, over and over again. And if you take something like, let's take, I don't know, maybe France or Germany. I think maybe like Germany is a good example. Some places were in 1700, and some places were, let's say, what's like the earliest? 1582. Depending on which city you live in, it could be one of it. Like, yeah, amazing, right? I'd love to go more into this, but like, just check out the website. Like, let's look at Switzerland, for example. I think Switzerland is a good one also. Switzerland also is like, some cities, 1798, some places in Switzerland as early as 1583. So it's like, imagine imagine you're just writing a letter to someone in a different city in the same country. Imagine the people actually dealing with taxes. What does that even mean? So yeah, fun, I would say. I would call this fun. Was it worth it? Well, as you can imagine, historians are not happy. If you have some kind of document and it says March 3rd, 1602, similarly to how you have a local time, the first thing you have to ask as a historian is, well, what city was this written in? Because depending on the city, not even the country, the city, it might be in a different calendar system. And because of that, there are missing historical dates. There are dates that simply don't exist, but there are also duplicate dates, as in multiple independent days that all map to the same date, right? It must be fun being a historian. Astronomers don't use this because when you're talking about hundreds of years, in order to like actually use, track comets and things like this, they all use the Julian calendar for obvious reasons, because then they don't have to deal with all this. And if you ever see this word proleptic, whenever you see proleptic calendar, I want to explain what this means. This is how your calendar app works in your computer. When you open it up and you scroll back to March 3rd, 1205, and it says that that's a Monday, or whatever it says, that doesn't mean anything. Because what they do is, a proleptic calendar means the modern rule set for a calendar, apply it backwards. So it's not useful for historians, right? It's not useful for anyone. It doesn't mean anything, right? But it's an easy way, because then you don't have to deal with this. Like, imagine if you had a properly accurate working calendar. When you scroll back, the first question the computer would tell you is, well, what city are we talking about? Right? Or it actually would tell you, like, that date doesn't exist. Like, what are you going to do? Okay, but that's then. What about now? I want to give you a word of caution, because I know as engineers, we see the new shiny thing and we want to switch over. An example of this is daylight savings. You keep hearing arguments about the fact that daylight savings is stupid and we should get rid of it. And I agree, it is a stupid thing, and from like an engineering perspective, it doesn't make sense why it must exist. But I want you to think about the consequences of if tomorrow the United Nations voted that daylight savings is out. It would mean for the next 400 years, you would have a bunch of code that is trying to figure out in which year, which city of a country decided to apply those rules or not, right? Think about that. I want to like bear into it that doing the engineering work is one thing, but convincing the entire world to do something is a completely different other story, right? Same thing with your API v2. We've all had this. You have a v2, you're already on v3. There's that one customer that refuses to get off v1. Was it worth it? That's a question only you can answer. Hiram's law, right? Anything the way the system works, is the documentation, is the specification, doesn't matter what you think, right? I think it's important to think about this before you release v1. Whether you are happy living with this v1 for the foreseeable future. How are we feeling? Are we still good? I think we're doing good on time. Okay, That means I'll have time to show you some C++ because that was a request from the audience. To rewrite or not to rewrite? That is the question. I'm not going to give you one of those bullshit it depends answers. I'm going to actually tell you there is an actual rule. This is Norbert's golden rule of rewriting. Rewrite if and only if you want to build on different principles. That's it. We can all go home. Are we convinced? What does that mean? The question is, what are principles? Principles, I want you to think about as well-defined things. Like, think of it like axioms versus platitudes, right? Axioms are, this is a single write database, single write or transactor database. CQRS splits commands and requests such that a read can never mutate state and a command is always fire and forget. It doesn't matter what the axioms are. You decide. But they have to be things that give you some kind of ability to scale up. As in, once these constraints, because that's the thing about creativity, the more you constrain your system, the more you can actually use it to your advantage. And the whole thing about building on principles is you define a bunch of axioms that you say, these are things that will always be true, I can always depend on it 100%, and because of that, I can use that information to make other kind of interesting architectural decisions. Platitudes, on the other hand, are things like, we will rewrite it using clean code. Or we will TDD the hell out of this application this time, right? Those are nice things to have. I'm not saying don't do it, but don't call that a rewrite, right? You're not giving yourself some kind of superpower to do things any differently this time, right? You do not simply like TDD or YOLO principles. These are things you have to think about very hard because what happens in the real world is this rewrite, it's going to take a year, maybe 2 years to actually get it into production and actually phase out the old thing. You're going to hit a hurdle where it's like it's no longer fun. There's a new shiny thing in there somewhere out there. You're going to hit the hurdle that your stakeholders are, why are we spending so much money on this? And at that point, you have to be able to point at those axioms, those principles you've defined in your system and said, this is why we're doing this. As soon as we finish this, we will be able to do X, Y, and Z. We will be able to guarantee things about the system that we couldn't before, and we will abuse that to our competitive advantage, right? Anything else? I would argue, let's just not call it rewrites. They're refactors, or sometimes they're just retries. Retries can happen two ways. You can be like, this team learned a lot about what happened, and they're just going to do a clean slate implementation. If they don't have that discussion about, these are the principles we're building on, it's a retry. It's just throwing things at a wall, maybe it'll stick. If you decide to hire a brand new team without all that domain knowledge to do it again, a retry. If you do 2 years worth of refactoring and fixing the tests and doing everything, that's really excellent work, but it's not a rewrite. It's just a very good refactor of your code, which I applaud. But if we stop calling them rewrites, maybe we wouldn't have these stupid discussions on the internet. I want to give you a thought experiment. This is the code. This is all you see. How long are we sleeping for? We don't know. 10 seconds, 10 days, 10 hours. What's the type? I mean, it's not a trick question. It's an integer, right? The type is an integer. So here's my question. You've got a 1,000,000-line code base, 100% test coverage. And you've got a bunch of places doing very complicated math that ends up being put into that sleep function. How confident do you feel in your system that you need to convert everywhere to go from seconds to milliseconds? From an integer to an integer, that means something else. And let me up the stakes. You don't feel particularly confident, but you've got an ego trip, so yeah, I can do this. And then I tell you, this software is going up into a Boeing airplane you're flying next day. Do you still feel that confident that you found all the places where you assumed seconds and it should have been milliseconds? Yeah, you're in the plane. That's actually, I think, also a nice principle is engineers should by definition be flying the things they build. That's what they actually mean when they said test in production. So reality check. We suck. We shouldn't be calling ourselves engineers, right? This is terrible, but this is what we do every day. Chrono is a C++ library written by Howard Hinand. He tried to solve this problem. And I'm giving it to you for two reasons. First, as an example of practicing what you preach, of using a small set of principles to do a fundamental rewrite of a system. And the second thing is, even though this library is in C++, the ideas behind this library, I think, are things that we should adopt in every single programming language, because they just fundamentally do time better than anything else I've seen. And Howard Hinand has believed in these principles so much, he has gone through 4 C++ committees to get more and more of his library into the C++ standard. And if you're not aware, on some arbitrary spectrum, deploying leftpad to NPM is here. Getting something approved by the C++ committee is here. It's as far as you can get the other way, as far as the amount of just crap you have to do to convince a bunch of people to put something in a standard that's not even a single implementation, that's multiple implementations of the C++ compiler, right? By a very conservative number of people who don't want to change anything ever. And he did this 4 times. So what was the problem statement? The problem statement was he wants this safety that I just talked about, but he can't in any way impact performance, because any change to performance means that no C++ developer will use it. So it won't go into the standard. He came up with a specific solution, which is type check units, compile time ratios, generics, and standard library algorithms. But that's just one solution. He could have come up with a different solution, right? The point is that he understood very clearly, these are my goals. This is the sort of Lego blocks I'm choosing to solve them with. And I'm going full steam ahead, right? And I won't stop until it's in the standard. So what is chrono in practice? Well, the first thing is, one of the things it defines is, it defines a duration. So a duration is time elapsed. And as you can imagine, it is not an integer. Instead, it's a representation of some value and a ratio compared to seconds. The representation can be anything. It could be int, float, whatever, because it's specific to the code you're writing. But the ratio is always to seconds. Seconds, it turns out, is a really good system to use as a baseline. Because as I talked about previously, on the very first slide, that feels like 3 hours ago, every day has exactly 86,400 seconds, right? What does this mean in practice? You can define things like milliseconds, micros, nanos. They're just different ratios compared to a second. But you can define arbitrary things like 60 FPS. You can define it as a new type that you just use in your code, or NTSC frames, right? These are all just ratios. All they're saying is, I have a very specific relationship to what a second, for what a 1 second means in time. And the way the library works, this is like, this is sort of like idiomatic because it's C++. We wouldn't do the same thing in Ruby. But my point is, in C++, what he ended up doing was, if the function assumes that you need a duration of float in milliseconds, and you pass in 5 frames of 60 FPS and 45 milliseconds, everything that's happening on the bottom there, the compiler is doing at compile time. It's checking all of the semantics, that all of these numbers that you're trying to add together are something that you can do without any kind of implicit conversion that would break the semantics. Here, the conversion is allowed because we're using a float at the end, so we're already losing technically data, but this is a loss that the programmer understands because he wrote the function. But what's really interesting is that this all happens in compile time. All this kind of semantic checking, type checking. At runtime, this is just these are just basically a couple numbers that are getting multiplied and added, which is the exact same code that which is like the exact same code the programmer would have written, hand-coded, to get the most performant version. So you get the exact same performance, or better, than what the human would have written, but you get all of the compile time semantic checking, right? And the next thing is, he said, well, time point is not a duration, because it's a moment in time. You can't say something like some number of seconds, and it can't mean a specific point in time because it's relative to some starting point, right? This is just like that problem with the epoch. So he just defines a time point, which is the duration we just talked about, with a clock. And the clock explains what is the starting point and like what are the ticks, right? Like what does it mean to be +1 of a clock? And then you can define lots of clocks, like by default the library. It gives you like all the constant kind of clocks, like system clock, steady clock, atomic clocks. But the thing is that the interface is so simple, you can define your own clocks that only make sense in your specific application or domain. And as long as you can explain it in terms of relation to seconds, you get all of the infrastructure for free to do it with everything else, right? And of course, ratios work both ways. You can get less of a second, but you can get more of a second. So you can get minutes, hours, and days. And then the natural question is, how many seconds are in a month? You don't know, right? Because? Because of the Romans. You're getting it. Square peg, round hole problem, right? Most calendar libraries get this wrong. That thing on the top, right? The 31st of January plus 1 month. If you check any of your favorite calendar libraries, it will do one of several things. It will either return the 28th of February, or if it's a leap year, maybe it'll return the 29th, or it'll return the 1st of March, or maybe it'll just assume a month is 31 or 30 days, so it'll come back with like March 3rd, or it'll throw an error, because what does it mean? You can't add 1 month, like what does that even mean? Or maybe it'll just like do, oh, it's actually February 31st. All of those are legitimate cases. I've seen in some, like, choose an arbitrary calendar library, it does one of those things. The point is that all of those answers are correct depending on context. The problem is that if the library implements it as the logic, it means that the programmer who understands the specific domain they're in can't choose the algorithm correctly. If you are working on tax software, your definition of +1 month is very different than you're working on Google Calendar or like scheduling emails or whatever, right? The point is that there is no one answer. The only way to win is to not play the game, right? Don't do auto conversions. Have the programmer tell you what they mean. And also this comes back every time you need to do a complicated logic, like you want to schedule something for every last Wednesday, unless it's the 5th Wednesday of a month, and then don't do anything, right? If your calendar library assumes that months are just 31 days, this kind of logic is really, really hard to implement. And the only way to solve this problem is the way Chrono does it, which is they say, you've got time elapsed, which is duration and time points, and then you've got calendars. And calendars have absolutely nothing to do with durations. They are some kind of class, like some kind of logic that defines what it means to have valid dates in Julian calendar or the Chinese calendar or ISO week or whatever, right? These are completely, this is a separate abstraction, right? You've got calendars and you've got durations and time elapsed. They're just different parts of the library. And then for convenience, you've got structs, but you could have just implemented this yourself. You've got some convenience structs because it turns out that very often in a specific domain, you work with a specific kind of structure. Like you think about things as just weekdays, or maybe you just count the number of weeks in a year, or things like this. And then if your structure is, I actually only care about what year it is and what week of the year it is, then it's a struct with 2 values, and it's really easy to do like a +1 operation on that because you find the week, property and you add +1 to it. And you don't have to think about the fact, like, what does that mean in time spent? Because you're working on the arbitrary semantics of your structure. You're not actually thinking about duration of time. And then the only thing that really needs to be done is at some point, you need to do that conversion. So I want to just jump to like this last point there on the bottom, which is, if you make your library allow for explicitly switching abstractions, this is the same thing with that Christian Zeller calendar, where he converted the calendar to make it easy to work with the kinds of things he wants to work with, and then he converts it back. Similarly in Chrono, you can start with like a civil calendar, you can convert it to duration days, you can then do a bunch of stuff you were trying to compute, and then maybe you end up switching it to an ISO week standard, right? The point is that these steps need to be explicit because they're specific to your domain. Don't try to hide this stuff in the library. So I kind of jumped to the end of that slide, but in general, the retrospective for Chrono is, notice how there was a very minimum number of principal abstractions here. I would love to talk more about the fact that Chrono actually, the part related to time and not to calendars, is also really nice and interesting, but this is something you guys have to go check out for yourself. It actually also covers things like daylight savings time and all this stuff, but it implements it by adding it as a layer on top of this logic. So it's like you've got time and duration as a concept. On top of that, you've got calendars, which is independent, but there's some functions that help you switch between these things. On top of that, you've got a layer that talks about things like daylight savings time, because that has nothing to do with calendars and duration. That's something about how, you know, specific laws were passed in specific countries. You can build these kinds of abstractions as long as you start thinking about this as independent abstractions. And it also helps us to teach us about doing things like avoiding exceptions. So months are not a special number of days. Calendars are not duration days. And what's really interesting is in Chrono, there is no such thing as like a special leap year. They just explained that just the same way you have a leap year every 4 years, there's something called a leap century, which happens every 400 years. And it turns out that you don't need a bunch of ifs, because when you call it a leap century, you don't need that weirdness between 400 and 100, right? You know exactly when it happens. So the really nice thing about Chrono is that, and the thing I sort of didn't hammer maybe home so much, is that once you have these constraints, and it limits you on the way you can convert between things, you can let the computer do a lot of interesting algebra and a bunch of semantic checking that you otherwise wouldn't allow. So if you just had integers, all of this would fall out the window. But once you have these concepts, you can do things such as, if you take a time point and you subtract another time point, you will get a duration, right? Because it's 2 moments of time and how much time has passed between these things. If you take a moment in time, a time point, and you add a duration, you get a new time point. But if you take a time point and a time point and you add them together, what do you get? An error, because semantically it doesn't make any sense. And while it was an integer, it could have been easily a bug. And the thing is, not only do you get these guarantees, but because of the fact that the computer understands all this stuff, it lets you automatically do a bunch of conversions that right now you're hand rolling, right? We talked about the fact that the best way to avoid bugs is to write less code. This actually lets you write a lot less code, because you let the computer do all the hard work of understanding those relationships. And anything that you can do without sort of losing information, it will do by default. This is the end of my talk. You have been a wonderful audience. If you want to learn more about time and calendars, I suggest you go and watch some YouTube or read some white papers from these people. If you care about time, and I think we should all care about it, I think you should really study the Chrono library. It has a lot more stuff than I talked about here. But yeah, I mean, time limit and all. Programming. Avoid overexcited hype. But also avoid, grumpy naysayers like me, right? Like, I'm also not right. I'm more often wrong than I'm right. But I do encourage you to study the past. It is amazing how often new research comes out in the sense of, oh, we just read this paper from the 1970s and we implemented it. Because back then, we didn't have the compute power, but it turns out that now we do, right? And it's amazing how often you learn about weird things you do every day because of some decision that happened, 2,000 years ago. If you care about performance, don't assume, always measure. And remember that computers are changing. In 5 years, all these slides are out of date because we're all on some GPU computers, and in 10 years, we've got quantum computing, right? When you're building stuff, this is sort of like my thing is, this is why we're talking about C++ at a Ruby conference. I think the point is that you should learn to embrace this idea of going to other programming communities, taking their root essence, like taking ideas that they have and stealing them and just implementing in a way that makes sense in your community, right? So I encourage someone to study Chrono and implement a Ruby idiomatic version of this library, for example. If you go down the road of rewriting, do think about axioms and principles. And I can't believe I have to say this, it's 2025. But don't vibe code critical thinking, right? Your LLM would not be able to solve any of the problems we talked about today. That's all I've got. Thank you for your time.
Thank you, Norbert. Any questions? Anyone wants to roast some Romans? All right, they will come after in the after party. Thank you for your talk once again, Norbert Wójtowicz.